Ladies and gentlemen, thank you very much for your patience, and I'm very glad to see almost 90% full hall here at Hacktivity 2012, and we have reached our last presentation for today, I mean in this hall, and I'm very glad to announce Mr. Sandor Nagy and some figures. It's 6 o'clock, he's got 45 minutes. He's got 15 years of experience in IT security, and I think these figures must show something for us tonight. And I wish you a very nice presentation. Sandor, please.
Thank you for joining this presentation late in the night. We will see shortly whether it was your time. I hope so, at least. Actually, this presentation is about the NAT attack. What is it? As all of us know quite well, during an online attack, one of the main goals of the attacker is to hide his identity, to hide his location. Or better to say, or to be specific, to hide his real IP address. There are several ways to do so, but going not too far from the network layer, the primary candidate could be for this job is IP spoofing. IP spoofing is simple. All of us know. IP spoofing is simple. In this case, if the attacker uses the IP spoofing technique, he just sends out IP packets with so-called spoofed IPs. I mean IPs, IP addresses, that is different from his real IP address. So IP spoofing is easy, and it fits quite well to a number of attack types, like denial of service campaigns, or the mmap style idle scan, or the Mitnick attack, for example, or with IP spoofing, for example, zombie networks can be controlled remotely. So IP spoofing is quite it can be used quite well in many cases, but IP spoofing has a real disadvantage because it's a one-way communication channel. The problem is that when the target, when the other end replies the received packets, the reply packets are sent out to the spoofed IP. So the reply packets are delivered to the node that actually owns the spoofed IP, not to the attacker. So it's a problem, at least for the attacker's perspective, because if he cannot establish a two-way communication channel between the attacker and his own node, a bit more sophisticated attack cannot be launched. Just a simple example. For example, a SQL injection cannot be launched without a TCP connection. So this should be fixed in some way, and NAT attack can fix this problem. Actually, NAT attack is sort of IP spoofing. At least in case of a NAT attack, the two ends, the attacker and the victim, communicates with spoofed IPs, not the real ones, at least in some level. But NAT attack NAT attack is able to establish a two-way communication channel. So in our case, the attacker and the target can communicate to each other with spoofed IPs. And the third really important point is that the IP that appears on the target side as a source is not a proxy IP. So it's important that there is no requirement that there should be somewhere in the internet should be a node, a device that really owns this IP. That could be or not. It doesn't matter from the attack's perspective. So how NAT attack works? The first thing that should be highlighted that in case of NAT attack, the traditional network address translation protocol is, or the technique is, can be or should be used. And of course, it requires the manipulation of a network router. But this router can be anywhere in the internet. It doesn't a requirement that it should be on the path between the attacker and the target, the victim. It can be anywhere in the internet. So the concept of the NAT attack is quite simple. But first of all, what are the actors? There are some. This is the attacker. It's simple. This node is the attacker. So from this node, the attacker wants to connect to the victim. In this terminology, wants to connect to the virtual target, to the actual target, in a way that his real IP, this real source IP, is hidden. And the other actors, to build the NAT attack, to establish a communication channel in such a way, we need other actors as well. First of all, we need a network router. It's a so-called seized router, and it's under the attacker's control. So the attacker needs to take control over a network router. Yes, you are right. It's quite a big job. How it can be done. We will go back to it later in the second part of the presentation. But for now, we just accept that in some way the attacker is able to take control over a network router somewhere in the internet. And there are two other actors that's important from the attacker's point of view. First of all, there is another actor, the so-called virtual target. Actually, it's in this case, it's a physical node, but in practice, it's just an IP address that can be accessed from the attacker's node through the seized router. So if the attacker sends out network packets to the virtual target, these network packets are delivered through the seized router. And the last actor is the virtual source. The virtual source is also an IP practically, and this IP needs to be accessed through the victim, through the actual target, through the seized router as well. So practically, if the victim sends out IP packets to the virtual target, virtual source, sorry, in this case, the network packets goes through the seized router. So that's these are the actors, and just have a look how this attack, what the preparation is needed to implement this attack. First of all, we need a vulnerable router. So the attacker scans the internet to find vulnerable routers somewhere. It doesn't really matter where is this router. The attacker just needs one. How it can be, in the second part of the presentation, it's going to be covered in more details. And if a vulnerable router is found, the attacker tries to take over the router's control. And for the attack's perspective, we assume that he succeeds, and the control is in the attacker's hand from this point. And it's also a precondition of the attack that this router that's taken over, it is able to do network address translation, of course. The next step is, if the router is under the attacker's control, is to find or to select a suitable IP address that can be accessed from the attacker's node through the seized router. So it's just an IP address, the attacker chooses a suitable one. And the attacker also needs to choose another IP address that can be accessed through the victim, from the victim through the seized router as well. And this other IP address is the virtual source IP. And the last step of the preparation is to define the network address translation rules. In this, to make the attack works, the attacker needs to define the source IP network translation for the source IPs, and network translation for the destination IPs as well. And it's quite simple that the attacker's IP needs to be translated, the virtual source IP into the virtual source IP, and the actual target, the victim, needs to be translated to the virtual target IP. These network address translation rules should be defined on the router, and if it's done, all the preparation is finished, and the attack can be launched. What is the goal? The goal is to establish a two-way communication channel between the attacker and the actual target, the victim. So the best thing is that we go through. The best thing is to describe this procedure is to go through a TCP connection establishment. As all of us know, if a node initiates a TCP connection, the node sends out a SYN packet, and the other end, the target of the connection, replies with a SYN-ACK, and then finally, in the connection establishment phase, the initiator node sends out other TCP packet to finish the connection establishment. But from this point of view, we just focuses on the initial SYN packet and the SYN-ACK, the reply packet, and all the things goes in the same way later. So first of all, the attacker sends out a SYN packet. It's an IP packet, of course, and the source address in this phase is the attacker's real IP address, of course, and the destination address is the virtual target's IP. So an IP packet is sent out, source is the attacker's IP, destination is the virtual target. Because the virtual target IP is selected in such a way that all the packets from the attacker goes through the seized router, in some point in the delivery process, this IP packet is the seized router receives this IP packet. And the received router recognizes that there is a NAT address translation rule that should be applied to this packet. So the network addresses in the IP packet is translated according to the network address translation rules. And in this way, after the translation, the seized router sends out the packet with a destination IP, that is the victim's IP, and with a source IP, that is the virtual source IP. So according to these new IP addresses, the router sends out the IP packet to the right destination, to the victim's direction. The victim receives the IP packet, the SYN packet, and checks the IP addresses, and the victim recognizes that the source of this packet is the virtual source IP that is different from the attacker's real IP address, of course. The victim sends out a reply packet, a SYN-ACK packet, and this SYN-ACK packet has a source IP. It's, of course, it is the victim's IP, and the destination IP is the virtual source IP. And because the virtual source IP is selected in such a way that all the IP packets from the victim goes through the seize router. So in the delivery process, in some step in the delivery process, the seize router receives this IP packet. And the seize router also recognizes that this packet should be address translated. The NAT rule fits to this packet. So the seize router change again the IP addresses. The source IP is translated or exchanged with the virtual target's IP. And the destination IP is changed to the attacker's node. So, according to this procedure, the seize router sends out the reply packet to the right direction, to the attacker's direction. So, and finally, the attacker receives the reply packet. So, so a two-way communication channel is going to be established with this connection establishment packet exchange. So that was the procedure in the concept of the procedure. And the highlights are that a TCP connection can be established, and the victim, the actual target, knows nothing about the attacker's real IP address, and the IP address, the virtual source IP that the victim believes to communicate with can be any IP. I mean, there is no need to have a real physical device in somewhere the network. With this IP address, it can be anything. Maybe there is a physical device with this IP, maybe not. It doesn't really matter from the perspective of the attack. The point is that it's not a proxy IP. So the concept looks good, but what about the practice? There is a proof of concept setup. Actually, it's implemented in a virtual environment. With graphical network simulator 3. This tool is for the router's simulation, and also use VirtualBox for the computer's simulation. And this proof of concept setup is established in this virtual environment. And what are the roles? First of all, is in this case, PC null is the attacker. PC null is the attacker, and R1 is the seized router, and of course, PC2 is the victim in this case. And we also need two other actors. A virtual source and a virtual target. Actually, the virtual source is, in this case, is a physical device with this IP, but the virtual target is not exist in this particular case. The virtual target is another IP, but to be specific, 200.20.20.160. It's not an existing IP, it's just an IP that's going to be used. Because there is no need to have this IP, no need to be a physical device with this IP, so it can be used without a problem. So that is the environment. And of course, we are interested in the router configuration. Well, this is the router configuration. We need destination NAT, and we also need source NAT. The destination NAT is a bit longer, The blue the blue lines defines the destination net, and the source net is the green one. Of course, there are some overlapping regarding the interface configuration, but the points are assigned with these colors. There is an interesting part, this first line, the first blue line. Actually, this command, this configuration command, is actually intended by the Cisco, is intended to use for load balancing. So, and this command is applied for incoming packets. And with this command, we should define a pool of IP addresses that can the incoming packets can should be forwarded. So because it's it is for load balancing, we should define the first and the last IP of the IP pool. Generally, there is an IP pool and a number of servers, and the incoming packets are forwarded to one of them. In this particular case, it's used completely different purpose. With this pool, in this case, is just one IP, and so the first and the last IP of the pool is the same, and this is the victim's IP. So this is the victim's IP, and this is the new address, the translated address for the incoming packets, if the incoming packet has this IP, the virtual destination IP. So the virtual destination, the incoming packets received with this IP, this is the virtual destination IP, and if the IP fits to this rule, it's translated to one of the IP in the pool, and because it's only one IP in the pool, so it's translated to the victim's IP. And actually, that's the point. Of course, all of the other lines are so really important, of course, but that is the point from our perspective. So that is the configuration should be applied on R1. But if someone is familiar with iOS configuration, Cisco iOS configuration, may have or must have concerns whether this particular configuration works. Actually, it should not work, but in this particular case, it works. What is the problem? Actually, the problem is the net order of operations. So the router, in this case or in all cases, in case of a NAT, should do two different things. The first thing is to apply the network address translation, and the other thing is to make the routing decision. So, and if these operations in a particular order, it can make problems for the attack's perspective. So the point is that for incoming packets from outside to inside, the network address translation is done in first, and then the routing decision is made. So the address is translated and the routing decision is made. However, from inside to outside, first of all, the routing decision is made, and then the network address translation is done. And this is a problem because so back to the SYN-ACK packets. So from the for the SYN packet, there is no any issue. The SYN packet goes through the seized router, goes through the other router, and the victim receives the SYN packet. because in this case this router interface is defined as outside interface, and for the outside to inside packets, the network address translation is done at first, and then the routing decision is made, and the router forwards the packet into the right direction. But what about the reply packets? The reply packets are the router receives, the seized router receives the reply packets, and because the reply packet is an inside to outside packet, in this case, first of all, the routing decision is made, and the routing decision is that this packet should send out to this direction. And then after the routing decision, the network translation is done, and the packet is sent out in this direction with the source address of the virtual target, that's somewhere here, should be somewhere here, and with the destination address of the attacker. So fortunately, there is another router. There's another router, and his job is to send out the packets to the right direction. So in this case, the packet sent out in the wrong direction, but this is another router, and the packet sends back to the right direction. And from these packets, there is no NAT rules, so the seized router forwards the packet to the direction of the attacker. So this thing can be called as response reflection, and response reflection fix the issue that comes from the order of NAT operations. So however, it's not a nice solution. Of course, in this case, we are fortunate. It's a good thing for us that in the right direction there is another router. So in this case, to this response reflections, to do this response reflection things works, we need an extra router in this direction. And this extra router, there is no need to the attacker takes over its control, but the attack requires that this router should be in the right place. So it's not a nice solution from the attacker's perspective. But if the attacker is more careful in choosing the virtual target, the attacker can fix this issue. If the attacker selects an IP, a virtual target IP, on the same direction, then its own node is located. In this case, there is no need of an extra router, just this seized router, and the thing works. So all the things, all the necessary things are in place. So, between the attacker and the target, there is a two-way communication channel, and how the attacker can use it. First of all, what an attacker wants to do. First of all, he wants to scan the victim. The victim has this IP, and this is the virtual target IP. So if the attacker wants to launch an nmap against the victim, the attacker needs to specify the virtual target IP, and in this case, during this, because of this configuration, the attacker is able to scan the victim. And what about for example, if the attacker wants to launch a web attack? In this case, the attacker wants to specify the virtual target IP, and the victim is going to be accessed. And in this case, of course, the victim believes that the source of this connection is the virtual source and not the attacker. So it looks good. But in practice, there are some pitfalls for the attacker because of two things: the TCP problem and the NAT is applied for any communication. To be specific, because of the problem is that the problem is that the destination NAT is applied for TCP connections only. For TCP connections only. So in case of a TCP connection, the address translation, the destination address translation is done. And otherwise, in case of other protocols, the destination NAT is not applied. And the packets are delivered to the virtual target, not to the victim. So first of all, the attacker needs to know that he needs to use TCP connections, and if he wants, for example, ping the target, he needs to use some other alternative ping solution. The other problem is more serious for the attacker, is that the source NAT works for any protocol. So if from the victim a traceroute is launched to the virtual source, in this case the traceroute goes to the attacker's node. So that is the attacker's IP. So if the attacker wants to cope with this, wants to fix this issue, the attacker needs to block this communication, for example, ICMP echo request packets on the seized router. So there is a blocking condition should be applied. So there's pretty much only a short time ahead. So we should make a step further. One of the most important most important step in the attack is taking over a router's control. So we need, or the attacker need a router, and if he succeeds to have one, he can launch the attack. There are several ways how a router can be taken over. For example, there are binary attacks. Actually, binary attacks are really difficult. So we should, or the attacker wants to choose the easy way. And what would be easier than a dictionary attack? So, is there any chance of a dictionary attack? Actually, the problem with the dictionary, dictionary attack is not a sophisticated thing. Dictionary attack is really simple, but quite effective. So we are interested in whether dictionary attack can be applied in network routers. So we are interested in, but don't want to invest too much work to disclose this thing. So first of all, we need to look around whether there is some research somewhere that already covered this problem. Actually, if we look around, we can find a really interesting research. Two guys from an American university made a really wide-scale scan, and the goal of this wide-scale scan was to find embedded devices that can be accessed by default passwords. So, and the result was quite interesting. They found 4 million in-scope devices, and more than 500,000 devices can be accessed by default passwords. So the question is whether this research can be applied for our case. Unfortunately not, because This research has a much wider scope. They investigated any type of embedded devices, but from the NAT attack perspective, we are interested in just network routers. So it's a great result, but cannot be applied for our case. So we need to make our hands dirty and do some scan, some own research. So first of all, we want to launch, or the attacker wants to launch a dictionary attack, and the precondition of a dictionary attack is that some remote network interfaces like Telnet, SSH, HTTP, HTTPS should be accessed over the public internet. The problem is that from the attack's perspective, that in case of a well-managed router, in case of a well-managed device, these remote control interfaces must not be accessed from the public internet. So in a perfect world, dictionary attack has no chance. But just look around. There are poverty, there are wars, people starving, and there are stupid politicians, so we don't live in a perfect world. So what about the network routers from this from this perspective? Well, we need to launch a scan, and the purpose of this scan is to find potentially vulnerable devices, network routers, and we want to give an estimation about the whole number of the vulnerable routers in the internet. So a really simple scan was conducted. This scan or this procedure consists of 3 steps. First of all, we need to gather router IPs. So we want to investigate routers, so we need router IPs from somewhere. Next, we need to check whether these devices with these routers can be accessed by through the remote communication channels, SSH, Telnet, and so on. And finally, we need to check whether these devices that can be accessed by these remote channels, whether these devices are protected by ACLs, access control lists. So the results are as follows. First of all, gathering potential router IPs. So we need just a really rough estimation. The procedure was to gather potential router IPs are quite simple. We just need to use traceroute to randomly selected IPs and pick up the nodes from the traceroute outputs. With good probability, these nodes are router IPs. Of course, not all of them, but there are some router IPs. We just want a really rough estimation. So from our point of view, it works. So at the end of this step, nearly 10,000 devices were found. Next step is to identify whether these devices have publicly accessible, whether these devices can be accessed over HTTP, Telnet, and so on. And a really simple thing can do this. Nmap and just the well-known ports are specified. And this command is applied for all of the IPs that's collected in the previous step, and more than 600 IPs are identified, devices are identified that can be accessed at least with one remote access port. Next thing is we've got more than 700 devices that can be accessed over Telnet, HTTP or something like that. And we need to check whether these access points are protected with access control lists. So even if these ports can be accessed from the public internet, but maybe there are access control lists, and even in this case, if we connect to these ports, we've got a problem because cannot connect to it, cannot launch this dictionary attack. So the procedure was quite simple. With a suitable client program, just need to try to connect to this port, and if a logon prompt appears, in this case there is no access control list, and otherwise access control list is applied. So this is the results, and the main thing is that more than 300 cases that are open accessible ports are in place that can be accessed through these remote communication protocols. But because HTTP and HTTPS generally have limited functionality, so we should focus on these nearly 300 IPs, and in this case we can say that these devices are maybe potentially vulnerable to dictionary attack. If we, so this is the nearly 3% of the whole devices that investigated, that checked. So if we make an estimation about the whole number of potentially vulnerable devices in the public internet, we have a result that about 5 and 10,000 routers can be potentially vulnerable regarding this perspective. But there is a small, or not too small, thing that needs to be taken into account, that even if these devices can be accessed over these remote access protocols, maybe account lock is applied. So in this case, if there is a predefined number of failed logon attempt, in this case the account is logged and the dictionary attack fails. So we need to find which devices are probably not protected by the account lock. And if we checked again the previous results, it can be found that about nearly 60 cases there was no any attempt on the router side to ask for the username. In this case, only the passwords are asked, and in these cases, there is a good chance that the default installation is applied on these routers, and in this case, there is no account lock is applied. So in this case, nearly 60 cases, these devices are a good target for a dictionary attack. So what is the point from this perspective? There are some estimations that 10,000 routers are vulnerable, or 1,000 routers are vulnerable for dictionary attack, and so on. These estimations are a good thing, but the point is that even if these numbers, these estimations are completely wrong, but the point is that it was really easy to find devices in the public internet that can be a valuable target of a dictionary attack without account lock. And time is up, but there is another thing. Maybe if you download the slides, there is a really brief summary of the binary attacks. There is a timeline, and some good references about the binary attacks and the other aspects of this presentation. Thank you for your attention.